Hello everyone. My name is Abhishek Bansal. In this video, I am going to talk on the I am going to discuss and talk on the flyback converter. I would be taking how the flyback converter is derived in this form of circuit configuration or circuit diagram, which is basically essentially and derived from the buck boost converter only. And I would be talking on the mathematical operation of the continuous and the discontinuous mode. This video would be related only to the flyback converter operation and its derivation, except for the one point, like similarly I have taken in the buck boost video also. One point I have taken in the buck boost converter, and here also one point I will be taking why it's called a flyback. That would be only used in the flyback quantity video. This video rest would be dedicated to its operation and the derivation. So this is now let's start with the flyback converter. This is I have drawn a flyback converter here. This is the input source. We are having a DC. I am taking a DC only. We input is a DC only. Here I have put an RCD snubber circuit. It's a transformer here. These are two dot ends of the transformer, and here a switch is connected. Here I have taken the switch to be a MOSFET here, and again a diode and a capacitor, and then we have an output voltage. So what we are basically seeing in this a flyback converter is that we are having a switch that is connected to the transformer primary, and when this switch is on or when the switch is is closed, when the switch is on or when the switch is closed, the transformer is going to store energy, okay, during this t on time, and it's going to provide an isolation between the input and an output. Moreover, this dot end of the winding becomes positive with respect to the to the non-dot end, and the diode D1 becomes reverse biased. That means the circuit here will get open, and the output load current, the output is going to take only from this capacitor only its load supply requirement, the current requirement. So during this t on time, the transformer is behaving as an inductor only and storing the energy, and during this time only the current is going to rise linearly like in the buck or a boost converter rises from IL1 to IL2, or we say that's an I peak here, and the value of this inductor is equal to the transformer primary magnetizing inductance and the stored magnetizing energy. Now as this at the end of the t on time, that is when the switch is now turned off, the switch is getting an open. Since it's an inductor behaving as an inductor transformer, it has an inductance property. It cannot instantaneously change the magnetizing current value. Rather, now this dot end becomes what? It induces the magnetizing current. It induces the negative voltage in the dot end. As the result of this, diode becomes forward biased, and it completes the path, circuit path. The stored energy which is in the inductor, it is given to the load. So now the important thing is that this energy which is stored in the primary, it is transferred to the secondary, and this happens through the action which is called the flyback action. And because of this only it is known as a flyback converter, because the energy which gets stored during the t on time or the when the switch is closed, the transformer was behaving as an inductor, the whole energy is transferred to the secondary through the flyback action, okay. And it not only providing an energy to the output load, it also charges the capacitance, because this capacitor provides energy during the t on time when the diode is becoming a reverse biased. Now we have to very much careful in this, in the forward converter that I won't be covering up because I have hardly used the forward converter, and though the half bridge configurations are based on that forward only. So this forward, like in the forward, when the switch was turned off, we need some current path basically to dissipate the stored energy in the magnetic core. We can use a snubber, or we can use a reset winding also. If we are using a reset winding also, we can the if I am using a reset winding, that reset winding is also going to forward bias the diode, and is going to reset the magnetizing stored energy. But here I am using a here I am using a particularly a snubber circuit. If I am going to use a reset winding, I may not use the snubber circuit, because the snubber circuit are meant to de-stress the semiconductors we are using it. If I am not using a semiconductor this snubber circuit, I have to use the MOSFET with a higher rating which can bear the stresses, because the snubber is going to limit the rate of rise of current during the t of time, and the rate of rise of voltage during the t on time. Okay, there could be a various configurations on the snubber itself. The main point is that here the snubber is basically working because now I said that there is no path to dissipate the stored energy or the stored leakage energy in the magnetic core of this flyback transformer. So what happens, this leakage flux which is stored in the magnetic core, it induces a positive voltage at this non-dot end, and this is going to forward bias the diode, and as the diode is going to get forward bias, the capacitor is going to get charged with some voltage, and in this flyback we talk of the reflected secondary output voltage. We are not talking of only the output voltage, we are talking of the reflected secondary output voltage, and the capacitor voltage can charge to more than the reflected secondary output voltage. I would be going on the reflected secondary output voltage etc. things in the designing example only. Like what could be the secondary voltage etc., and what would be the VDS for the MOSFET. Like here the VDS have to be taken care of, it won't be equal to only Vn, but we have to take care of this reflected secondary voltage also. It should be at this reflected secondary output voltage also, and that's the V clamp voltage and the leakage storage energy. So this capacitance can charge, will get charged as soon as the diode is going to get forward bias. The charging can be more than the reflected secondary voltage. It's going to cause it can cause a flyback overshoot, and the rest would be dissipated in the resistor. This is how basically the this number works it, because it allows to clamp the primary voltage. It has to be clamped to a safe voltage level. If we are not going to use this RCD snubber circuit, or I have mentioned earlier, like in the forward also converter we used to utilize a reset winding, this primary winding would be clamped to unsafe voltages. That's going to damage the complete circuit. Okay, so this is again the flyback overshoot. It provides additional volts to drive the current into the secondary leakage, and that's again the flyback action. So that's why this is known as a flyback converter or a flyback transformer, because it's going to use firstly is going to transfer the energy stored in the primary of the transformer to the secondary through the flyback action. Here we are getting a flyback overshoot, that's because of the reflected secondary output voltage, and it's going to clamp the primary winding voltage to a safer level, that's again through the flyback action. So we are having a what would be the meaning of the continuous conduction mode in this flyback converter when we are using a transformer isolation? We know that continuous conduction mode means the inductor current never reaches to zero, and that means when we are talking excuse me, when we are talking the continuous conduction mode in the flyback transformer, we are talking of basically an incomplete demagnetization of the transformer core. So what it is going to do it, the core flux is going to rise also from some linear from some IL from some phi1 value to a phi2 value, okay, or we can say the peak value, we can say here the flux is also going to rise, and in the steady state, the change in the core flux during the T-on period, it's equal to the change in the flux during the T-off period, and this is basically important to avoid the saturation. So that means when we are working in a continuous conduction mode, we are dealing with an incomplete demagnetization energy of the transformer core, and we have to avoid this, or we have to be very careful to avoid the transformer saturation, because the change in the core flux during the T-on has to be equal to the change in the flux during the T-off. Okay, I am just drawing roughly here what it means. That means if suppose I say the flux, I said it's going to rise it, let's say it's going to rise it here, or if I'm going to rise it this, so this curve it takes, it's causing the transformer to saturate, and this was only by the method that I've claimed, a self-claimed method to predict the transformer saturation, because the transformer saturation is the condition that we want to avoid during the flyback converter operation, the working circuit operation. We do not want our transformer to get saturated, and the transformer will get saturated. One reason is that when this change in the flux during the on and the off time are unequal, because otherwise it's going to cause this kind of peak here. Okay, that means it's causing a saturation. So now during this continuous conduction mode, the duty cycle is independent upon of the load, and is basically a constant for a DC input voltage source. Okay, the load increases the loss inside the transformer. If we are taking some particular output load, the load is going to increase the transformer losses, and also the output diode losses also would get increased. We have to maintain an output constant voltage, therefore we can vary the duty cycle to maintain a constant DC input voltage, not to at a constant input DC voltage. So now here we have the concept of secondary reflected voltage, because this voltage gets reflected on the secondary voltage. There is a leak stored energy in the transformer core, and it gets reflected back to the transformer primary. It gets reflected, that's what is known as the secondary is reflected secondary output voltage. The maximum stress is on the switch would therefore has to take this output voltage secondary into account into the equation. That means VDS has to take care. This MOSFET should be able to, besides the V input voltage and the V clamp voltage, that here it must also, we have to also include this reflected output voltage. Okay, I have drawn, I would be taking care during the, I will explain all this during the design example of the PWM converter. So this was basically a this is basically a flyback converter. Here one more thing is that we take an air gap flyback transformer, and that is because we want to reduce the chances of magnetic saturation. We do not want our converter to get that flyback transformer to get saturated, and the transformer, this will get saturated very easily because of imbalance in the flux core changes during the T on and the T off cycle. So that can very easily happen practically, because theoretically we can say okay, this is equal to that, but practically if it's something minor, it can accumulate, integrate the differences in the flux. The flux do not get cancelled there. So that's why we are going to use an air gap magnetic core that reduces the chances of the magnetic saturation, and this air gap is basically inserted in the limb of the transformer core. Okay, so the air gap doesn't change basically the flux density value, it only increases the magnetic field intensity. So that I will cover in the transformer core, different kind of cores that are used to design the transformer cores. Okay, SMPS cores. That time I will include an air gap core also. So for now the operation is completed. I now derive this flyback transformer from the buck boost topology, incorporating a transformer, and then I am going to go on the continuous and the discontinuous mode. So before we derive this, we should know that we are having a transformer here, and the transformer is basically we know that we are having a transformer in this manner. We can say okay, we are having a transformer here. Okay, if I just draw a transformer. Okay, now if I say this is an N1, this is an N2. This is basically a transformer, and we can say represent it by in this manner. Okay, we can draw the dots here, or if I want to draw a dot in this manner here. Okay, now this transformer is an ideal transformer. I have not taken any of the losses because the practical transformer is going to have a winding, is going to have a core loss, is going to have winding resistance and the leakage flux. The practical transformer, if I am going to take a magnetizing inductance into account, I would be including here a magnetizing inductance here, and if I am going to take a core loss, I can put in parallel the core loss with a resistor here into this magnetizing, that would represent the core loss. And if I have to take a winding resistance or the leakage flux, I can take a winding resistance here and the leakage flux here. Okay, so this is the practical transformer. Okay, this is a similar would be on the secondary side. We can have here. Okay, now but for power electronics we are taking we are only basically considering about this LM. Okay, we are not taking here the core loss. For simplicity, we are not taking the winding resistance, we are not taking the leakage flux into account. We are only taking one thing, which is a magnetizing inductance, and this value is basically very important for designing of the flyback converter. Okay, so we can, if we want more realistic, we can say we can add a core loss here. We can add a resistance of the conductors of the inductor, or we can say we can include the leakage inductance of the winding. So now now I won't take a snubber here at present. I am just want to explain the continuous mode, and I know that we have placed the switch in series with the transformer primary. That means, if you remember, I have placed here plus, minus, and instead of the snubber I am only going to draw the transformer primary. I am going to take into account this magnetizing inductance LM also. Here it's this thing, this is an LM, and if you remember, this was the circuit. Okay, and here I have put what, a MOSFET here. The only change that I have done it here the only change that I have done it here, I have removed the snubber circuit and I have placed the magnetizing inductance here. Okay, so rest circuit with the same, it is will be a capacitor here. Yes. So we have drawn so when the circuit would be on, this would be, MOSFET can be simply removed, it would be simply this thing only, and when it would be an off, I would be just drawing it. Okay, so now let's do the continuous conduction mode. So what will happen if the transformer gets saturated? It is definitely going to destroy or damage our circuit, because it is going to increase the currents that are not being taken care during the design limits, because the current would be very large. Obviously, it can cause very unintended or unexpected outcomes, very bad outcomes. It may cause fire also, and it will cause, definitely it is going to damage the circuit, and it may also damage other protection equipments. So that saturation has to be avoided. Okay, now again we can make a very same assumption that I have been making for in all the videos. Buck converter, buck boost converter, or a boost converter, we have taken the output capacitance to be very large. We are assuming a steady state condition. We are also taking the duty ratio of the during the on time is dt, off time is 1 minus d into t. The components are all idle. We are not taking any non-linearities. Okay, so when during an on period, so what is basically happening is here, what is the V1? Now let's take a V1. Now let's take it here, a V input. Let's put it V input. That means I input is equal to ILM, and this ILM is going to flow here. This voltage plus minus, this would be equal to, let's say, V1, and this would be equal to V1 only. Okay, now during an on period, I forgot here one mistake is done. During an on period, this would become open, this would be reverse biased. Okay, so I get to even remove the diode here, and during this T on period, that means we can say V1 voltage across this primary equal to V input equal to what? LM, because LM we have taken LM di by dt. We can very easily, like in all the previous converters we have been doing it, we will take LM here down here and find the rate of change of current. That means we are getting a V input here. V input upon LM is equal to di by dt, and this di is nothing but an IL upon delta t. Now we know what the delta t here, it was dt, so we can replace it by dt, and dt we can put it here. That means delta IL is equal to V input upon LM into dt. So this is our change in current in the transformer magnetizing inductance when the when the switch is on or the switch is closed. Okay, so this was the primary side. Now on the secondary side or on the load side, V2 would be what? N2 upon N1 number of turns into V input, okay, into V input, okay. So we are going to have Vd is equal to minus V0 minus Vs into N2 upon N1. This would be because, very easily we can say, because what I have drawn is there. I have drawn this primary, okay, I have drawn then the secondary. This was a Vd, if I have to say, this was V output. So this was V output. So Vd we can say it's a V output minus, this is what we have already said, N2 upon N1 into V input. So that's what I have subtracted it. This is an N1 only and this would be less than 0 because I have taken it minus everywhere. That means we can take a minus common and this we can put a plus here. That's obviously the negative only, and the diode is off. That means our I2 is equal to 0 only, which, okay. So when the switch is closed, current is increasing linearly in the magnetizing inductance. The current is going to increase in this magnetizing inductance, and there is no current in the windings of the ideal transformer in the model. So that's why this LM parameter here is very important, and we have to avoid the saturation of this transformer, because one point I have already mentioned that if the saturation happens, it's going to lead unexpected levels of current rise. The other thing is that the core is going to get, the flux is going to get increased. that's why it's getting saturated only. The other point is that it cannot support a voltage across the transformer winding. A saturated, if once the source core gets saturated, it won't be able to, or it cannot support the voltage across the transformer winding. So this is the so in the actual transformer, if we see, because it's now an open circuit here, the current in the primary is going to keep on increasing while no current is existing in the secondary winding. Now if I go for the open scenario, open switch scenario, that means I am having a plus minus. Here again I am going to draw an LM. Here the switch is open now. Here we are having a transformer primary, okay, and here we are having a transformer secondary, and it is going to close. It would be not an open circuit, not very closed circuit. This is a capacitor. Now this would be what? Minus V reflected voltage N1 upon N2. This would be our primary side voltage, and we will, the secondary or the load side, it would be minus of the V input, and this is a minus, this would be plus, and this would be plus, this would be minus. Sorry. So this is what the mathematical operation of during the switch open time, because the current cannot change instantaneously in this magnetizing inductance. So there has to be some conduction path or the current path, as I have talked in the beginning. The snubber is going to be used for that, and the current, this ILM, it enters the undotted terminal of the primary, and it must exit the undotted terminal of the secondary. So this is going to make our undotted terminal. The current enters through this path, undotted terminal. It must exit through the undotted terminal of the secondary only. The diode current is going to be positive. Okay. So I have already said the voltage, the secondary transformer voltage, the secondary voltage transforms back to the primary. It stabilizes the LM. Okay. So these are the voltages and the currents, because now we are having a reflected secondary output voltage along with the number of turns, and that is the primary voltage level. Secondary voltage level is simply, it would be equal to output voltage, sorry, and we can say V input or the V1 is equal to V2 N1 by N2, that we know, and now our V2 is what? Minus V0, so this will be minus V0 N1 by N2. That's why we have got this V1 primary voltage, which is basically reflected here. Okay. So let's take the magnetizing inductance also. Let me just repeat it, because we know that V1 is equal to V2 N2 upon N1 upon N2, and as our V2 is basically equal to now what? Minus V0, so it would be minus V0, and that is why this V1 is this voltage level minus V0 N1 upon N2. Now we know this will be equal to Lm di by dt, and I again here would be an Lm only, because we are talking of a magnetizing inductance, that is going to be equal to what? V1 I have set upon V1, and V1 I have already said it's V1 V0 n by n2. So we can equate the equations both, and we can again delta I, we can put dILM by delta ILM upon delta T. Lm we will take here, it would be minus V0 upon Lm n1 by n2. We know the switch was off for a period of what? We are taking always here 1 minus dt. We can replace 1 minus dt, and we can put then here 1 minus dt here, and t we can use as 1 by f frequency. So this would be our change in the transformer magnetizing current when the switch is open. So we have got the changes in the transformer magnetizing current when the switch is on or when the switch is basically off. Now as a steady state operation, we know what it happens. Off and on plus should be equal to 0. Okay, the off and on has to be equal to 0. That's why the net change in, that is the net change in the inductor current, is 0 over 1 period of steady state operation, or we have got delta I L M during the T on period, and we have got delta I L during an off period equal to 0, and we can put the values. We will know that it's V input dt by Lm minus V0 1 minus d t by Lm n by n1 by n2 equal to 0, and this both will be equal to, if I am going to solve it, this t will get cancelled, Lm will get cancelled, we get V input d equal to V output 1 minus d, and this is what we have got an input output relation. V output minus obviously n1 by n2, we have just taken it here, and that's how we are getting the conversion ratio d upon 1 minus d into n2 by n1. The thing that I have drawn solved in 1 second by logic explanation, here I have derived it by mathematical formulation considering the inductance, magnetizing inductance current. Sorry. So if I am going to take a discontinuous mode, that means if I am taking a discontinuous mode, it would be again a similar thing only, because in the discontinuous mode we are having the same thing that was in the buck converter. This would be dt, this is d1t, and this is t. Okay, and the secondary Is would be simple this way. Okay. So when in the discontinuous current mode, the current is going to increase linearly only when the switch is closed, okay, but when the switch is open, the transformer magnetizing current decreases to 0 before the start of the next switching cycle, okay. So this is what it happens, because in the continuous current mode it was not declined to 0. Now I want to the other equations are basically similar to that of the buck and the boost only, and the buck boost only. Let's see if I want to write them or not, but I want to give one more explanation of the derivation of the circuit. We knows that knows that I have drawn a buck boost converter in this manner. If you remember, the buck boost converter I have designed in this manner, the inverting buck boost converter, and I have said that I am going to derive a flyback converter from this thing. Now how I am going to do it? I have taken an inductor here, if you see. So I am going to design this inductor, and I am going to wound this inductor into two parallel wires. Once I do this thing, thus inductor becomes in this manner. Okay. The inductor becomes this thing, and now if I now here I can very easily remove this line and say that the windings are isolated now, and we can take what? We can do this one thing. We have the switches in series here. Okay, I can draw the switches here in series here, and if you see, that was only, and once I am putting the switch here, the diode would be in this direction. Okay, that means firstly I have taken a simple inductor. Now I have constructed this inductor using two wires with 1:1 turns ratio. Okay, and we have got this thing here. Here again the diode position is same only, because I have not changed the switch series. Okay, now the function of this inductor is unchanged only. If I am going to replace it by two wires or a one wire, and the parallel windings, they would become equivalent to a single winding layer of a larger wire, or we can say that the connections. Now if I am going to break the connections, we can say the one winding is used when this switch conducts, the other winding is connected to the diode. When this diode conducts, it is being used that time. So the total current again would be unchanged only, but now here we have distributed the current between the two different windings separately. Okay, and if we are going to put this switch here instead of here, I am going to put a switch here, and here I am going to put a diode here. Now this is basically a, now see the earlier the polarity was, when I have taken place the diode here, the polarity was this, but I have changed the polarity, the dot it is now here, and I can do this. So this is how a flyback converter can be very simply derived from the buck converter only, using the we are using an inductor from the same inductor. The magnetic field inside the inductor in both the cases, whether it's a one this inductor, or if I am going to do it 1:1, or I can even now say 1:n, if I am going to do, the magnetic field is going to be the same only. So this is a two winding magnetic device. We are representing using the same symbol, or it can be said as two winding inductor. And in this two winding inductor, we are also going to take into account of the magnetizing inductance. Okay, the one more thing that I would be using, or one more thing that should be noted, is that one thing I have already mentioned, why it's called a flyback. The other thing that should be taken care of the saturation, and the other thing which is that in an ideal transformer, the current the current in this flyback transformer, it does not flow simultaneously in both the windings. Whereas if we are taking a normal or any other or an ideal transformer, the current is going to flow simultaneously in both the windings. Okay. In this video, I am going to end this video here only. There could rest I would going to instead of writing equations for the V input V output, I would rather take some examples, or I am going to take a design example, and that would be more sufficient than this theoretical V input, because I am going to assume the load resistive, and the load is not going to be purely resistive. So all those equations V naught by R, it does not make any sense practically. So I am going to give some practical design examples. I will take notes from the Texas Instruments on the power integration, and maybe one or two more semiconductors. Okay, so now I end this video. Thank you.